Alright, so remember our brute force approach? It consisted of two stages. The first one was trying out each and every subarray, and this is why we have these two nested for loops, and we can say that the time complexity of this is big O of n squared. And the second stage was actually computing how many distinct integers there are in the subarray ij, which was big O of n. And this is exactly why the final time complexity was big O of n cubed. Now, in order to optimize brute force approaches, we are going to reduce one of the stages. We have the stage in which we try out each and every subarray, which we are going to see in the next solution that even this can actually be reduced with a smart observation. And then we have the stage in which we compute the number of distinct integers. So I'm going to start by reducing this one from big O of n to big O of 1. And I'm going to do this first by noticing that in this brute force approach, I have done a lot of extra work. We can use the fact that we are computing the number of distinct elements in each subarray in order to compute it faster. And let me tell you exactly how. For example, if, I don't know, n was equal to just 4, let's say, yeah? What did I do? I equals 0, j equals 0. So I have computed how many distinct integers are in the subarray 0, 0. And when I did this, how did I do it? Well, using the solution from number of distinct elements and basically having my hash table or my frequency array, doesn't matter. Let's say it's a frequency array and my counter, which was basically counting how many distinct elements there are and the frequency array for how many times each element appeared in the subarray. So when I have computed this, I already know its frequency arrays and counter. Then I'm going to move on to the next subarray, right? J is getting incremented, so I move on to subarray 0, 1. And now what I did in the brute force approach is that I started again from scratch. And in order to compute the number of distinct values here, I have started again with an empty frequency array with counter equals 0. And I have basically gone through these two elements. Okay. Then what did I do? Of course, I moved to the subarray 0, 2. And when I call this function, I start again fresh with an empty frequency array with counter equals 0. And I go through all the three elements. And then I move to 0, 3. And then to 0, 4, and so on and so forth, right? So you see what the problem is here? Why would I, let's say here, right? In order to compute the number of distinct elements here, why would I go again through each and every element from 0 to 3 when I have already gone through most of the elements on the previous subarray? So if let's say my array was this one, n equals 4, so 0, 1, 2, 3, and let's say, I don't know, I have the elements 1, 2, 1, 3, right? Now, when I have solved this problem and counted how many distinct elements are here, what did I do? Well, started with my frequency array, which is initially empty, right? So let's have a frequency array, let's say 0, 1, 2, 3. Had my counter, which was initially also equal to 0. And what did I do? First element, okay. This one became 1 and the counter became 1. Next element, 2. All right, this one became 1. It's a new element. The counter became 2. Next element, 1. Oh, I see that I already have a 1. I'm still going to increment its value. So it appears 2 times, but the counter still equals 2. And I have solved the problem 0, 2. Now, when I move to 0, 3, why would I throw all of this away and start off with an empty frequency array and counter equals 0, when the only difference between the subarray 0, 2 and the subarray 0, 3 is the new element. So what I should do is keep all the information that I've gathered on the previous subarray and just update it. What I can do is take a look at the next element. Okay, its value is 3. It has not been encountered. I'm gonna increase the counter and set its frequency to 1. And here I know the answer for the next subarray. Guess what? When I'm going to move to 0, 4, let's say there was another element here, for example, and its value was 2. Same spiel. If I already know the information for the subarray 0, 3, why would I reset it and throw it away? I'm just going to move to the next element. Its value is 2. It is already existent, so counter stays 3. and this one becomes 2. And this is it, guys. As simple as that. When we move from a subarray I, j, to the next subarray, which is I, j plus 1, all I should do is look at the frequency of my new element, and if it's 0, increase the counter, and then increment the frequency, and this is all. Now, there is also one scenario in which, let's say my current subarray was actually I and n minus 1, right? If it was I and n minus 1, for example, let's say here, 0 and 4, then the next subarray is going to be 1, 1, right? So in this types of scenario where from I n minus 1, the next subarray is actually I plus 1, I increment the starting point and also I plus 1, then yes, in these types of scenario, I should reset the frequency because I'm starting off with a fresh subarray. Unfortunately, I can't reset the frequency and the counter in constant time, so still big O of 1, but this is not a problem. I can even do that in big O of n. So I can make this transition in big O of n. And you know why is that? Because I'm making this transition for at most n times. So if this happens for at most n times big O of n will be big O of n squared. And if this transition, which is performed in constant time, again, I just check a frequency, increment it, and eventually increment the counter. This is done in constant time. And this happens most of the time. This happens for, let's say, n squared times. This is the upper bound. So if this happens for n squared times, I'm still going to have big O of n squared in total for this one. And with this smart optimization, our algorithm just became big O of n squared. Now let's take a look at the code to actually see how to make this transition in constant time and how to reset the frequency and the counter in big O of n time. Alright, and here is the code. As you can see, I use the variable answer, which is initially 0, and I return it in the end. And I use a hash table, which I named number of occurrences, in order to count for how many times each value appears in my current subarray. Now, I try out each and every start point I from 0 to n minus 1, and here, as you can see, I reset the hash table and the counter. Why do I do it here? Because each time we enter this for loop, we are basically done trying out each and every subarray for the previous value of I, so we will start with a fresh subarray, right? On the previous iteration of this for loop, where I had the value I minus 1, right? I have basically gone with all the values that j could possibly take. So in the end, I had the subarray I minus 1 and n minus 1, right? And when I finish the job for this left endpoint and I want to move to the next one, so the next endpoint is indeed our current I, and the first subarray is going to be I. Obviously, I shouldn't have all those values in the hash table anymore. So that's why we reset both of this here. And one more thing that is worth mentioning is that this might look like a constant operation, right? I'm just, declaring a hash table which is empty, but that's not correct. What we are doing here is that we are actually clearing the hash table. In the previous iteration of this for loop, on the last stage, I basically had the subarray I minus 1 and n minus 1, and all the values inside this subarray were inserted into my hash table, right? So I had those pairs consisting of each element from here along with its frequency. So even in the worst case scenario, if you think about it, how many elements are here in this subarray? N minus I. And in the worst case scenario, let's say each and every one of them appeared only once, so they were all distinct. This means that I had n minus 1 different pairs in this hash table, which I now have to clear. So our hash table behind the scenes is going to release that memory, is going to delete those pairs because I don't need them anymore. And deleting a pair is constant time, but deleting n minus I pairs is not. We are going to say that it is big O of n. So we will take an upper bound here. This is a very, very finesse thing. And trust me, it matters a lot during coding interviews. So after we have reset this, what do? Of course, we try out each and every value of j, starting from I to n minus 1. And inside this for loop, on each iteration, what happens is that I basically take a new value into my current subarray, right? So if let's say on, the first iteration, the subarray is I, then on the next one, the subarray is I plus 1, I plus 2, and so on and so forth, right? What happens each time when j got incremented is that this new element should now be taken into account because it might be a different one and the counter actually might get increased. So what will I do? I first check if the new element nums of j is not part of our hash table. So it is basically a new value. It hasn't been encountered in this subarray yet. And if so, I will, of course, increment the number of distinct values. And afterwards, I'm gonna increment the number of occurrences of this new element. I'm gonna increase it by 1. And don't forget about what happens here. Actually, two things happen. The first one, when we try to access it, is that we either already have that pair, so nums of j was part of the hash table, so we'll just increment its frequency, or maybe we don't have a pair with this key, so the hash table is going to create one for us with nums of j and its frequency 0, and then we increment that frequency, so we have the pair nums of j and 1, which is correct. Now that I've done these updates, and I know the number of distinct values of my current subarray, I'm going to check, of course, if this subarray is valid. So if counter is less than or equal to k, what I'm going to do is, of course, update the answer if the length of this subarray is greater than its current value. And this is it, guys. Now let us analyze the time complexity of this algorithm. And as usual, I'm going to start with the atomic operations. And what are they? Well, answer equals 0 happens only once and is constant. Awesome. The hash table, because it is empty and we just created here once, constant. I enter the for loop. Then what do? I know that this is big O of n because I'm clearing the hash table. This is constant, just an assignment. I have a for loop. Then what do I check? I check if this key is part of the hash table, which again, the searching in a hash table happens in constant time. So this is also constant, constant here. This we have an access and a modify, both constant. We check this constant. This one is constant and this also constant. Awesome. So first of all, let's start from the bottom, right? I have this piece of code, which as you can see, consists only of constant operations. So this is constant. Now I execute this code for how many times? For a total of n minus I times. Okay, let's write n minus I here to be specific. Then what happens here? I have this piece of code, which as you can see, big O of n and the constant, it will be big O of n. And I have this for loop, which performs a total of how many n iterations, right? So this is interesting. I enter this for loop n times. So for a total of n times, I execute this piece of code, which is big O of n. So I already have a big O of n squared from this. Then I enter this for loop, and inside it, I only do constant stuff. And I do it for n minus I times. So yeah, we can compute a specific number, but because we already have this big O of n squared, who's going to be part of our time complexity, it's easier to just say this is less than or equal to n. So let's say that for n times, I execute this constant thing. And of course, be very careful, these n times also happen inside this n times. So for a total of n squared times, I execute this constant code. So yeah, I will have another big O of n squared, which is, of course, not going to be taken into account. And the final time complexity of the algorithm is big O of n squared. Awesome, guys. So remember, in a lot of problems, we are going to compute some information for a subarray based on the fact that we have already computed the information for the previous one. This is super important. Now, let's get to the serious stuff and see how we can apply the two pointers method in order to make this algorithm big O of n. I'll see you there.